All right. So next week, right now, so 7 days, we'll be starting the test. Okay, so make sure you're here early for that. Today and next Tuesday, we will be moving on into kinetics. Next week is a review of thermodynamics in the discussion. There was an issue with homework number 3. I forgot I had it so that you could do it late. So I extended homework number 3 until 2:25. Okay, so you have those 2 homeworks. One you should have already done, but the other you can. Okay, so all right, last time we talked all about the tests, no notes allowed. You'll be given no equations. So in the stuff, if you need equations, you need to memorize them. One thing is I posted under part 1, under modules, so modules part 1, I have a practice test and its answer key. I have the overview slide, so that's the end of each section slide that I put up. Discussion worksheets 1 through 4 are there with their answer keys. I will post up worksheet number 5 next week. Next week in discussion, there'll be a worksheet or something to go over, but I also tell the instructors to leave some extra time, right? So the last 20, 30 minutes will be just for questions. So bring them with you. All right, talked about this. These are the opportunities in office hours and in tutoring to get help between now and next Thursday. Okay, so you can see office hours. Office hours, just drop in during those times. If they don't work, email me or ask me any questions via email. Tutoring does change based on the things. So sometimes it's in University Hall. Sometimes it's in the temporary office buildings, which are over there. And then it's also in the library sometimes. So, okay. Questions? All right, let me just. All right, so last time, so this is stuff that's not on the test. Okay, test number 1, it will be on test number 2, obviously. So we talked about kinetics, and kinetics is all about the speed of the reaction. And so the first thing we talked about was the reaction rate. So you can talk about how fast a reaction is occurring based on how the concentrations are changing in a specific number of amount of time. So this is in molarity often, per second, or per minute, or per hour, depending on how fast or slow it is. We then looked at some examples of reaction rates, and we came up with some rules to think. So the rates are always the change in concentration over change in time. They are always positive, meaning that if you're talking about reactants lose concentration, so therefore you need to have a negative sign in front. If you're talking about products, no minus sign. Reaction rates can vary with time. Okay, so for instance, the slope of these 2 curves signifies the rate. Okay, so you can see at the beginning the slope is steeper, so that means they're faster reaction rates. Over time, in this example at least, they slow down. We talked about 3 different types of reaction rates, or how to calculate them. Average is over some amount of time. So for instance, if I want to know from 0 to 200 seconds, that will give me the average. The instantaneous reaction rate is at any given time. And so this is actually, if you make that time interval smaller and smaller, And then it's just the slope at any given time. And then we talked about the initial reaction rate. The initial reaction rate is the reaction rate at time 0. And the last topic we talked about was relative reaction rate. Okay. The reaction rates are related based on the stoichiometry of the reaction. Okay. So 1 over A, the coefficient in front of reactant A times its rate is equal to 1 over B, the coefficient in front of B times its rate. And so we looked at this last time. We said, okay, what if I'm told that the reaction rate of ammonia consumption and H3 consumption is 0.6 molar per second? And I want to know what the rate is for for O2. Well, the rate of O2 divided by 5 is equal to the rate of NH3 divided by 4. And I get those from the balanced chemical reaction. Okay. I rearrange that to get that the rate of O2 is 5/4 times the rate of NH3, or 0.75. Okay. The reaction rate for the O2 is faster because the stoichiometry has a bigger coefficient in front of it. Questions? All right, let's have you all do these problems. Okay, so the same problem, except now we're asking for the rate of NO and then the rate of H2O. I have the example for O2 right there, so you should be able to figure it out. Okay. That's 1 over 5 times the rate of O2. What number goes there? 1 and 4. Okay. Now rearrange it. Okay. Once you plug in what goes underneath 1 over blank, right? Then it's just rearranging. Then it's a problem you have done since you took algebra. Okay. In this case, it's 1 over 4 times the rate of NO. You never learn this in algebra. You never had the algebra teacher say rate of NH3, right? But you did this type of problem, right? You know what NH3 is, right? 1/4 times 0.6 equals 1/4 times the rate of NO. So solve for the rate of NO. If I want to get rid of this 4, so I multiply by 4. That's 4 times 4/4 times 0.6 equals the rate of an NO. The rate of the NO is going to be the same as the rate of the NH3. That makes sense because for every 4 NH3, you produce 4 NOs, right? So 1 to 1. So that means their rates are going to be the exact same, right? As one gets consumed, the other gets produced. That's not going to be the case for the last one, H2O. Question back here. Can you move around that roster? Question. Exactly, right? I need to get to your ones I had before. Because you know information that. Because you want something that says rate of H2O equals stuff. What number goes here? 6. And so then I want to know H2O production. So I want something that says rate of H2O equals blank. So I want to multiply by 6. So I get 6/4 times the rate of NH3, which is 0.6. And so that gets me 0.900 moles per liter second. So when the coefficients are the same, the rates are the same. When the coefficients are different, the rates are going to be different. Okay. Why? Because as you use up the NH3, you produce more H2O. Questions?
If you write it in like the fraction form, either the 1/4 and the 1/6.
Because that's how they're related. Like that's the only way to say it, right? It's always that they're related based on that coefficient, right? You could say rate of A divided by the coefficient. So you don't need to say 1 times, but that's the same thing. All right, now there's one last thing, the overall reaction rate. So we talked about the reaction rate in terms of each one of these compounds. Well, if we want the overall reaction rate, what we do is we just take 1/4 times the rate of NH3. Right? So I take the reaction rate for that. And so that's 1/4 times the rate of NH3, which was 0.6. So the overall reaction rate would be 0.105 mole per liter second. And I can do this for any of the other compounds, right? I have there in A that the rate of O2 is 0.75. So I could say that the rate is equal to 1/5 times the rate of O2. So that's 1/5 times 0.75, right? What I've got for O2. And what do I get? I get the same answer. Okay. So the overall reaction rate is any of the reaction rate for any of the compounds divided by its balanced stoichiometric coefficient. I could do the same thing with H2O, right? 0.9 divided by 6 would get me the 0.15. All right, so those are some rules for talking about reaction rates, okay? The first is the change in concentration over the change in time. It's always positive. It can vary with time, and we can relate the reaction rates for each of the different compounds. All right, now let's go on and let's talk about some factors that affect rates. Okay, so the rate of reaction can change based on certain factors. All right, do you guys remember in Chem 2100, there's a lab where you would put different metals into water, okay? And sometimes you'd see little bubbles, right? Sometimes, and in fact, you guys didn't do it, they did it at the front of the class, you would see some fire, right? So the first factor affecting rates are that the compounds involved affect it, okay? So you have a very similar reaction, but with a different compound, and the rate, the speed of the reaction can vary, right? So for instance, solid sodium with water is very fast. Calcium, if you put that in water, it's still going to react, but it's slower. It's not going to produce fire like this guy is. The second factor is that if you take the reactant and you subdivide it, so if you crush it or if you well, usually crush it, turn it into a little powder, it's going to react faster. So here's an example. This is iron in acid. Okay. If you put the iron in as a little powder, it reacts very fast. If you just put an iron nail in there, it's fairly slow. You guys are used to this, right? If you want to put some like sugar into your into lemonade, right? You kind of grind it up so it mixes in there. If you just put a chunk, it's going to take time for it to all dissolve. Okay, so the smaller the subdivision, the faster it will be. The third, again, you guys know this, temperature. Typically, if you increase the temperature, it speeds up a reaction. Not always, but typically. This is why in lab, you have a hot plate. This is why if your turkey isn't done and you have to feed people in an hour, you turn up the temperature, right? This is also why we use refrigerators, right? The milk is having reactions involving bacteria, and that's why it goes bad. Well, what do? You put it in the refrigerator to slow down all those reactions. If you leave the milk out overnight, you probably want to just pour it down the drain when you get up in the morning, right? Depends, but yeah. The fourth factor that can change a reaction rate is the concentration. Typically, the higher the reactant concentration, the faster the reaction. Let's have this. A plus B, so the black circles and the red diamonds reacting to form C. Okay, so in order for A and B to react, they have to actually come in contact, right? So the more of B there is, the more likely it'll come in contact with the A and cause a reaction. This is also why reaction rates can vary with time. Okay, let's go back to the example we showed earlier or last time. If I have this reaction, A going to B, at the very beginning, here I have 10 A's, here I have 8 A's. So if I lower my concentration, that means it's less likely to occur, so my reaction rate goes down. All right, the fifth factor is catalysts. Catalysts, and we'll talk more about these later, are substances that increase the rate of reaction without being consumed, right? So for instance, if I have NO and I run it over a piece of platinum, it can be converted into O2 and N2. The platinum is just acting as a catalyst, right? It's allowing this reaction to occur, but it's not getting eaten away, right? Or being consumed. Anyone have any idea where this occurs? This exact reaction with that catalyst occurs probably in over 50% of the cars you drive, right? You have a catalytic converter. That catalytic converter has platinum in there, and your engine produces NO, it reacts on that platinum to produce N2 and O2. Okay, this is why air quality in the United States is much better than it used to be in the 60s, right? Because of things like catalytic converters. This is also why, I haven't heard as much about it now, but last year I saw it like road signs, etc. People sometimes steal catalytic converters, right? Because they want to get that platinum. Okay. All right, a lot of you are biologists. What are catalysts in the body called? Anyone know? Enzymes, right? So enzymes, which are fundamental for life, are catalysts, right? And that's why it's so important to talk about. Okay, so that is an overview on reaction rates. We talked about some rules for it. We talked about the factors affecting the rates, right? And so always remember that the rate is how concentrations change per unit time. Questions? Did everyone get the roster? Anyone not get it? All right, we used a little bit of math so far, but not a lot. So now let's go ahead and do some calculations involving reaction rates. All right, so what we're going to talk about now are what are called rate laws or reaction rate laws. We'll just call them rate laws. Yeah. Rate laws are an equation linking the rate of a reaction with the concentration of reactants. All right, so let's say we have this reaction. A plus B goes to C. And I have the coefficients in front of it, right? Those are the small. So the rate law give me 1 second. Right here. Oh. All right, so the rate is equal to K times the concentration A to some power M times the concentration of B times some power N. Notice that the power they're raised to is not the coefficient itself. Okay, so it's raised to the power M and N, not necessarily the small a and the b. Okay, also notice that the rate is not dependent on the concentration of the products, only on the concentrations of the reactants A and B. All right, so it doesn't depend on D. M and N are the what are called the rate order with respect to A and to B. K is a rate constant. Okay, K is a rate constant that is experimentally determined. Now, K depends on how the rate is defined. So if we're looking at the rate of A loss or B loss or C formation, it'll be different. M and N are also experimentally found. We do not know the value for M and N based on the balanced equation. But M and N are integers, zeros, or fractions. The overall order is M plus N. All right, so rate equals K times the concentration of one of the reactants to a power times concentration of another reactant times another power. If this were a reaction with 3 reactants, we would then have a term for C raised to another rate order. All right, so the first thing we're going to talk about are what are called differential rate laws. Differential rate laws link the rate to the concentration of the reactant A. So the rate equals negative delta A over delta T, right? And that equals K times the concentration A raised to some power N. If we do it in such a way that delta becomes really small, we will get D, or differential. All right, so we have that rate equals negative dA dt equals K times the concentration of A raised to some power M. All right, so let's look at some data. All right, so let's say we have this reaction. 2NO2 plus F2 goes to 2NO2F. We're told, based on experiment, that the rate equals K times NO2 times F2 squared. By the way, just one math thing, because I could see this being written. When I have it like this, F2 squared, that's just the concentration of F2, not the entire thing. Okay, so it's like K times NO2 and then times F2 squared. Okay, I've never noticed that before, but I want to make sure. Okay, so what is the order of this reaction with respect to NO2? So what we do is we look at this and we see what power NO2 is raised to. Okay. Well, we don't see a number there. Okay, so what is NO2 being raised to? 1, right? 4 raised to the power 1 is just 4, right? So NO2 raised to the power of 1 is NO2. So NO2 has the order 1. How about the F2? 2. Okay. How about NO2F? NO2F. Is it in that equation? Right? So it's not. So F2 is 2. So we say that NO2F is raised to the power of 0. Why is that? Well, any number raised to the power of 0, and you can try this on your calculator, 4 to the power of 0 equals 1. Okay, so just plug in any number, raise to the power of 0, you get 1, right? So if it's not in the rate law, we call that 0 order. All right, what's the overall order here? 3. Okay. 1 plus 2 equals 3. So this is a third order reaction. All right, but notice that I gave you that rate order, right? I gave you that it was rate equals K NO2 times F2 squared, right? How do we actually determine that rate law? That's what we're going to do next, okay? All right, but before I do that, I want you to notice something. NO2 is raised to the power 1. What's the coefficient in front of 2? The NO2. 2. Those aren't the same thing, right? F2 is raised to the power 2. The coefficient in front of it is 1. So the coefficient and the order aren't the same thing, okay? Because based on the equation, you might think it's NO2 squared, but it's not. Okay. So let's go through how we determine the rate laws. All right, so let's say we have this reaction. NO2 plus CO goes to NO plus CO2. The rate could be K, so rate equals K times NO2 times CO. Or it could be K times NO2 times CO squared, or K NO2 squared times CO. Or we could have something where we have 0 order, so it might be rate equals K times NO2 and rate equals KCO. There are a lot of different possibilities for what the rate law could be. There are actually a lot of other possibilities. It's actually possible to have half orders, okay? But for the most part in this class, you'll see 0, 1, or 2. You might see some that are 3 or 4, but usually we don't do those, okay? So just remember, it's probably 0, 1, or 2. Okay. And again, it's not dependent on the coefficients in the equation. All right, so let's go ahead and let's use this equation. Rate equals K NO2 squared times CO. And let's say K is equal to 0.1, right? K is called a rate constant. What does it mean to be a constant? It doesn't change, right? So it's a little bit false because it can change based on temperature, but this is a rate constant. Okay, so if we want to speed up the rate, we can increase the rate by increasing the amount of reactant. We can't change the constant because that's a constant. Okay. So we could increase CO or NO2. NO wouldn't have any effect. All right, let's look at the CO first. Okay, CO is first order. So if I have 2 molar NO2 and 3 molar CO, my rate would be 0.1 times 2 squared times 3. Actually, let's be a little more. It's 2 molar squared times 3 molar to the 1. All right, so if I do the math, 2 times 2 squared is 4 times 3 is 12, and times 0.1 would get me 1.2. Yes. How do I get that 2? Right? We'll get into that in a little bit. Okay, but for now, we're just using rate laws and understanding them. Okay, but we'll get to that in a second. Okay, so rate equals 1.2. What if I double the amount of CO? Right? So now my rate would be what did everyone get? 2.4, right? So I went from, so I doubled my concentration of Cl, and notice what happened to my rate. It also doubled. Okay, so if you have a first order, so something A, so just compound to the 1. If you multiply A by X, your rate increases by X. What does that mean? If I double it, so if I increase it by 2, my rate goes up by 2. If I make it 4 times bigger, my rate goes up by 4. If I make it half as much, my rate goes down by half. Okay, so being first order means that, yeah, this exactly, right? Okay. Let's say if it's second order, okay? So NO2 is second order. We already did this calculation for 2 and 3, right? So we said rate equals 0.1 times 2 squared times 3. So we got 1.2. What if we double the amount of NO? Okay, so now I have 0.1 times 16 times 3 equals 4.8. Notice, I doubled my amount of NO2, and did my rate double? How much did it go up by? 4. It went from 1.2 to 2.4 to 4.8. So if I double, it goes up by 4. Well, let's remember something. 2 squared equals 4, right? So for second order, if you multiply A by X, the rate increases by X squared. Okay, so if you multiply it by 2, it goes up by 4. If you multiply it by 3, this goes up by 9, right? If it goes down by half squared would give you a quarter. Okay. All right, let's say we now have something that is zero order. Okay. If I have that rate equals, so if I have 2 molar NO2 and 3 molar CO, I can get this for the rate. Well, what if I double the amount of NO? Does anything change here? Right? The amount of NO2 doesn't change and the amount of CO doesn't change, right? So doubling the amount of NO or tripling it or whatever does not change your reaction. Okay. So if you have something that is zero order, increasing A has no effect on the rate. So even if you add a lot of it, if it's zero order, it's going to have no effect on the rate. Okay, so if you have zero order, no effect. First order, A to the 1, it increases just by X. If it's A squared, right, multiply A by X, rate increases by X squared. If you had, and again, I said, hey, we're not going to see it that much, right? But if we had A and it was third order, if I multiply it by X, the rate would increase by X cubed. Okay. So if I double it, it would be 2 cubed, which is 2, 4, 8. All right, so I'm going to ask you guys these, right? So let's say we have this reaction, A plus B going to C. Again, we're just using generic compounds, it doesn't really matter. So if the rate law, if I tell you the rate law is rate equals K times A times B squared, and I told you the initial rate is 1.2 molar per second. What will be the rate if I double A or if I triple B and then if I double A and triple B? Okay. You have to think about what order each one of those is, A and B. So A is first order. If I have it first order, if I double it, 2 to the 1 gets me 2. So I multiply by my rate by 2, and I would get 2.4 molar per second, right? Doubling A, which is first order, double the rate. Heat is second order. So if I increase the concentration of B by 3, what do I do to the rate? It goes up by how much? 3 squared, which is 9, not 6. It's a, if you're doing stuff on tests, I've seen it a lot where it's like, oh, 3 squared, it's 6. No, it's 9. So we do 3 squared, so it goes up by 9. So if it was originally 1.2, it will become 10.8. What happens if you double it and double A and you triple B? Well, both of these will happen. Okay, so if I take A to the first and B to the second, so if I take 2, which is how much I'm increasing A by to the first, and 3 squared, that'll get me 2 times 9 or 18. If I multiply that by 1.2, I get 21.6 for my concentrate or for my rate. What happens if I quadruple the amount of C? Nothing. C is a product, it's not in my rate law, so it has no effect. What if I increase the amount of compound D? No effect. If it's not in the rate law, changing the concentration will have no effect on our rate. All right, now let's talk about the rate constant. Let's talk about K. By the way, in this class, in the 2200 and in chemistry in general, we use K a lot and we use C a lot, right? We already saw this because we had big C and small c, right? In this class, a small k is the rate constant, okay? In about 3 weeks, we'll learn about big K and we'll talk about the rest of the time. That's an equilibrium constant, okay? So small k is a rate constant. And if I could change it, I would, but they've been using small k for this for like a century, so we just have to deal. All right, so let's say we have this equation. or this reaction, NO2 plus CO goes to NO and CO2. We are given, right? We're not finding it out, but we're given that rate equals K times NO2 squared times CO. And we do an experiment with this, and we find out that NO2 is 3 molar, or so we start off with 3 molar NO2, 2.4 molar CO, and we end up with a rate of 0.56. So let's figure out what K is. So we know the rate is 0.56 molar per second equals K times 3 squared times 2.4. And these are molarities. All right, so that'll be 0.56 molarity, second to the minus 1 equals K times 9. So 3 squared is 9, and molarity squared times 2.4 molar. So now that's equal to K. 9 times 2.4 is 21.6. And then I have molarity squared times molarity. So that's molarity cubed. All right, we want to find out what K is. So what would we do to this? Divide by the 21.6. So I get that K equals 0.56 molarity seconds minus 1 over 21.6 molarity cubed, whatever the hell that is. So 0.56 divided by 21.6 equals 0.026. I have molarity seconds minus 1 over molarity cubed. So I can cancel one of these out. So I'd get molarity to the minus 2 seconds to the minus 1. And molarity to the minus 2 just is 1 over molarity squared. All right, so notice that, so we should know some things. The concentrations that we use, the ones in brackets, for this class, not always, for this class, we're going to use molarity. It will always be molarity. The rate will always be molarities per second. Okay, so what that means is the units of K will change to make it work. Okay, so in this case, the units of K are molarity to the minus 2, seconds to the minus 1. If I have a different rate order for my reaction, it will be different. Okay, so for instance, if I have a 0 order rate law, so rate equals K, well, if my rate is molarity per second, that means my K has to have units of molarity per second. Okay, if it's overall first order, All right, if it's first order, so something like rate equals K times A, or rate equals K times B, or rate equals K times C, right? Overall first order, the K is in seconds to the minus one. Why is that the case? Well, because I said rate is molarity per second. And if K and the concentration is in molarity, right? That means that the K has to be in seconds to the minus one. Okay. If it's second order, well then K equals rate over something like A squared. So if this is molarity seconds minus one over molarity squared, the K is going to be in molarity to minus 1 seconds minus one. Okay. And that's just to make the units work out. Okay. There's nothing other than that. Okay. All right. What about if it's third order? What do you think it is? It's molarity to minus 2 times seconds to the minus 1, right? So as your rate order increases, what happens is you need to have molarity more in the denominator. Okay. You can either work out the math or you can just memorize it, right? So for zero order, it's molarity seconds minus 1, then seconds minus 1, etc. Okay. All right. So let's have you all do this equation. So let's say we have rate equals K times OH squared. And we're told that we have 0.045 molar OH. And it reacts with an initial reaction rate of 0.00062 molarity seconds minus 1. What is the rate constant, including units? So I just plugged in the data. I rearranged it to get K equals something, and then it's just math. But remember, dimensional analysis means if we do the math operation, in this case, it's squaring it and then dividing, right? We're also doing that to the actual units. So my calculator gives me this. Those started off with 2 sig figs each, so my answer should have 2 sig figs. Remember, on the test next week, which right about now you'll be finishing or hopefully already done, right? Sig figs matter, right? But also units matter. So I have molarity, seconds to minus 1. Over molarity squared. This seconds to the minus 1 just means it's actually in the denominator, right? It's just molarity over seconds molarity squared. So I cancel out this top molarity. And this 2 becomes 1. And so I can say this as either, so this would be 1 over molarity seconds or molarity to the minus 1 seconds to the minus 1. All right. So to the negative 1 just means it's in the denominator. Okay. All right, so that is it for our first section on rate laws. Okay, remember that we have that the rate equals K times the concentration of the reactants to some order. Okay, next time on Tuesday, we'll start talking about how we determine what those orders are. Okay, so far all we've been told is this is the order. Okay, but we're going to actually determine those. Okay, all right, any questions? I'm going to just put this up one last time. Was there a question?
Yeah.
So there is a homework due on Tuesday, right? There won't be one due the following Tuesday. Yes. So you do not have to, I should say it. The rate laws will cover more of this on Tuesday. You will not cover it in discussion until after the test. And the homework won't be until like 2 weeks after the test. So don't think you have to cram too much of this right now. Hi, how's it going? Give me 1 second. All right.